Alright, welcome to section 6.5. This video will cover examples 1 through 4 in your notes. You'll learn how to plot complex number in the complex plane and find the absolute value of these numbers, and write the trig form of complex numbers. So we've been plotting real numbers on the real number axis since 2nd, 3rd, 4th grade. You can also represent a complex number, a plus bi, as a point a comma b in the complex plane. So this horizontal axis we refer to as the real axis, whereas the vertical we refer to as the imaginary axis. So if we're given this complex number, 3 plus 2i, I see the 3 is the real, and the 2i is the imaginary. So to plot this point, we go over 3 in the real and up. So the absolute value of this complex number is defined as the distance between the origin, which is always 0, 0, and the point AB, in this case 3, 2. So here, I see my horizontal distance is 3, my vertical distance is 2, so applying the Pythagorean theorem, I see the absolute value of 3 plus 2i would be the square root of 13. So when a complex number is strictly a real number, so we have, for example, 3 plus 0i. If we were to plot that, we'd go over 3 on the real and up 0 on the imaginary. So this point here, the absolute value of this complex number is simply 3. All right, so example 1 says plot the z equals negative 2 plus 5i and find its absolute value. So again, I see my real is negative 2, my imaginary is 5. So let's go over negative 2 on the real and up 5 on the imaginary. Plot that point and label it as 2 plus 5i. So the magnitude, again, is the distance from the origin to this point. So if I were to draw a triangle, so I could apply the Pythagorean theorem, I would have 2 to the left, 5 up. So the absolute value of negative 2 plus 5i is equal to the square root of negative 2 squared plus 5 squared, which comes out to the square root of 29. And again, this absolute value will always be positive. All right, go ahead and try exercise number 11 in your notes. Make sure you will plot it in a complex plane and find its absolute value, so the value will be a positive number. Check your answer in the back of the book. Come back when you're done. All right, back in section 2.4, you learn how to add, subtract, multiply, and divide complex numbers. So to work effectively later in this chapter with powers and roots of complex numbers, it's helpful to write a complex number in trig form. So let's first consider a non-zero complex number a plus bi, which is plotted here as a comma b, and let theta be the angle from the positive real axis to the line segment connecting the origin to the point a plus bi. Now, similar to chapters 3, 4, and 5, let's draw a triangle that uses this theta here. So drawing from our knowledge of SOHCAHTOA, I could say that cosine of this angle theta is equal to adjacent over hypotenuse, so in this case a over r, cross multiplying, I get a is equal to r times cosine theta. Similarly, I can see that sine of this angle theta is equal to b over r. Cross multiplying again, I get b equals r times sine theta. In our previous example, we saw that r value is equal to the square root of a squared plus b squared. We know that any complex number can be written in the form a plus bi. Well, making this substitution for a, we get r cosine theta plus b is r sine theta I. Factoring out an r, we get r cosine theta plus, we're going to put the I in front so it doesn't get tied up into the theta argument. So I sine theta, close parentheses. So this is called the trig form of of the complex number. So similar to when we were looking at vectors, we have that the tangent of theta is equal to b over a. This number r, the distance from the origin to the point plotted, is called the modulus, and theta is called the argument of z. Worth noting that when we put it into trig form, we say z is equal to the trig form. Sometimes you'll hear the trig form of a complex number also being referred to as polar form. Now, because there's infinitely many choices for theta, we normally restrict theta on the interval from 0 to 2 pi. But there are times when it is convenient to choose a negative theta value. For this course, we will be strictly working between 0 and 2 pi. All right, so for example 2, it says write the complex number z equals negative 2i in trig form. All right, so let's remind ourselves what trig form looks like. So we've got z is equal to r, open parentheses, cosine theta plus I sine theta. Well, here, looking at this given problem, I see that my real part is actually 0 minus 2i. So plotting this, I just need to go down negative 2 on the imaginary axis. So this must be the point 0, comma, negative 2. So things we need. We need, of course, our r value, and we need our theta value. Let's see, r is equal to the square root of a squared plus b squared. Our a value is 0, and our b value is negative 2. So when we square it, we get an r value of simply 2. Now, we also need theta. So tangent of theta equals b over a. So my b value is negative 2. My a value is 0. So tangent of theta is undefined because it's division by 0. So if we take the inverse of this, for what value of theta is tangent undefined? Well, that happens at either pi over 2 or 3 pi over 2. But because we plotted the point, we can see that theta must be 3 pi over 2. So to actually answer the question, to get this in a trig form, we say z is equal to my r is 2, open parentheses, cosine, 3 pi over 2, plus I sine 3 pi over 2. A couple things worth noting before we move on. Remember, your r is always positive. It's always going to be a length of a segment, and your thetas will always be the same. All right, go ahead and try exercise 23 in your notes. Make sure you plot it, find r, and then put it into trig form. Check your answer in the back of the book. Come back when you're done. All right, example 3, we're asked to write this given complex number in trig form. So, quick reminder, trig form looks like z is equal to r, open parentheses, cosine of theta plus I sine theta. So things we need include the r, which is always positive, and this value of theta, which will always be the same. Before we go after those, let's draw a quick sketch of this complex number. So I see my a is negative 2, so I'm going to go over negative 2, and then down negative 2 root 3 is my b value. So I'm going to draw a quick triangle here. So I know I need my r value, and the r value is the distance from the origin to this point plotted. So I can say that r is equal to the square root of a squared plus b squared. Well, my a was negative 2 squared plus my b value is negative 2 root 3 squared. So underneath the square root, I've got 4 plus, let's see, 2 times 2 is 4. Root 3 times root 3 is 3, so 12. So it looks like my r value comes out to the square root of 16, or r comes out to 4. The other thing we need is, what is this value all the way around to theta? So we can say that the tangent of theta is equal to b over a. filling in values, we've got my b value is negative 2 root 3, all over my a value is negative 2. Let's cancel those negative 2's. So tangent of theta equals root 3. Let's take the inverse. So for what value of theta does the tangent come out to root 3? So theta must either be pi over 3 plus pi n. And I add pi n because of the length of the period of the tangent function. Well, clearly we're working in quadrant 3, and pi over 3 is in quadrant 1. So if we add 1 pi, we get theta as being 4 pi over 3. So now just substituting in values, we've got z is equal to r, 4, open parentheses, cosine, 4 pi over 3, plus I sine 4 pi over 3. Box your answer. All right, go ahead and try exercise 29 in your notes now. Do make sure you plot, find r, use the fact that tangent of theta equals b over a, and then give your answer in trigonometric form. Check your answer in the back of the book. Come back when you're done. All right, in example 4, we're asked to convert this complex number that's currently written in trig form into standard form of a plus bi. And this really isn't too bad to do. Let's just work from the inside and evaluate cosine of negative pi on 3 and sine of negative pi on 3. And also, let's go ahead and simplify that radical of square root of 8. So z is equal to 2 root 2, open parentheses, well, cosine of negative pi on 3 is 1/2, plus I, sine of negative pi on 3 is negative root 3 on 2. So let's distribute that 2 root 2 to each of those terms. So first I see that this 2 cancels with that 2, leaving me root 2. Second distribution, I see that this 2 cancels with that 2 in the denominator, leaving me root 2 times root 3, or negative root 6. So z equals root 2 minus root 6i. And we've answered the question. All right, go ahead and try exercise 47 in your notes now. Evaluate cosine of 120, sine of 120, distribute that 2, check your answer in the back of the book, come back when you're done. All right, go ahead and try the wrap up for examples 1 through 4 in your notes now. Number 1, plot the point on the complex number plane and find its absolute value. It should be a positive number. Make sure to simplify any radicals if you need to. Number 2, plot the complex numbers. I see in standard form z is equal to 0 plus 3i, and then write it into trig form. So refer to your notes what trig form looks like. For 3, write the complex number z equals 6 minus 6i. I would probably start by plotting that. Then find your z and find your theta. And lastly, on number 4, write the complex number actually, instead in trig form, write it into standard form a plus bi. Have a great night. I will see you tomorrow.